In the last video, we explored efficacy, affinity, and potency, as well as dose-response curves. But in this video, we're going to learn about different types of agonists, such as full agonists, inverse agonists, and partial agonists, as well as antagonists. We're going to learn how they work on receptors to affect the responses of a cell. Let's get into it. Okay, so in the last episode, we covered that messenger molecules are also known as agonists or ligands, and they bind onto receptors on cells or inside cells in order to produce responses. But how did this work? How does a messenger molecule binding onto a receptor allow the cell to have a response? Well, firstly, it's important to understand that receptors are types of proteins. There's lots of different proteins in the body, they make all sorts of things, they make up enzymes, but receptors are one type of thing that is made of proteins. And one important characteristic of protein is their conformation. The conformation basically refers to the protein's physical shape. And the reason the physical shape of a protein is important is because a protein's shape equals its function. Depending on what the conformation or what the shape of the protein is, that determines what functions it can do and what characteristics it has. And a change in the shape of a protein can cause a change in the function. So if you change the shape of the protein, it can change what the protein does, what it interacts with, what it can do. And that's exactly what happens when a ligand binds onto a receptor protein. It changes the conformation and the shape of the receptor so that it can have different functions and it can do different things. Okay, so let's say you have a receptor protein with the following conformation, with a little tail sticking out of the cell. Then a messenger molecule comes and binds to your receptor. When it does, it initiates a change in the conformation of your receptor, the shape of your receptor. As you can see now that your messenger molecule is bound to your receptor, the tail is now inside your cell, so there's a change in the shape, change in the conformation of the receptor. Now remember that with proteins, their shape equals their function. So now that there's a change in shape, now there can be changes in the function of this receptor. So this can unlock all sorts of possibilities. Ion channels can open up, allowing for ions to enter the cell, or perhaps it can interact with proteins inside the cell, such as G proteins can come, and those can go and activate other, enzymes to produce second messengers like CAMP or DAG, and those can produce responses. So all sorts of responses can happen now that your receptor protein has a change in conformation. It unlocks all these new functions and all these new possibilities. Okay, so now we know that agonists bind to receptors and responses happen inside your cells. But with any good story, if you have an agonist, you gotta have an antagonist. And you also have to have good side characters like full agonists, partial agonists, and inverse agonists. But what are all these things, antagonists and all these new different types of agonists? Well, in order to understand all of these concepts, we must first understand something called constitutive activity. See, the way that we've been looking at cells and receptors and responses up until this point hasn't been completely accurate. All this time, we've talked about basically when a cell is at rest, there is zero response happening inside the cell, it's just chilling, and then a messenger molecule will come and bind to the cell, and that will cause responses to occur inside the cell. But that isn't exactly true. You see, even when a messenger molecule is not bound to your receptor, so the receptors are free, there is still some level of response inside the cell. There's still some activity, and this is called constitutive activity. But you can think of it as like your base conditions or like your default settings. Even when nothing is bound to your receptors, it's free, the cell is just at rest on its own, there's still some activity, some response happening inside the cell. And this activity is called constitutive activity. So in order to better understand the concept of constitutive activity, let's take a look at a dose-response graph. This might help visualize it a little bit better. Here is a dose-response graph. Now, if you want to learn more about dose-response curves and dose-response graphs, be sure to check out my last video. I'll link it down in the description below. But, as you can see, this line here, it represents the constitutive activity of the cell. So here's response level on your y-axis, right? And as you can see, 0 is down here. So when the cell is at rest, when there's no agonist added, the cell is just by itself, then the response level is not at 0. It's up here. In this case, it's at 4. And this represents the constitutive activity at the cell. So when nothing's acting on the cell's just chilling, it is at this response level. Okay, so then when you add an agonist, what happens? Well, like we said, it binds to your receptor proteins and changes the conformation so that more response can occur. So response levels will increase above constitutive levels. So going back to our dose-response diagram, we've established that this line is constitutive activity when we don't have any agonist, but now when we add agonist, it goes and binds to receptors, activates them, and increases response. So that would make a dose-response curve something like this. So as you add concentration of your agonist, so you add more and more agonist, concentration increases, slowly response starts to increase, and then it starts to pick up, and then it increases very sharply, and then as you continue to increase concentration, the response increases at a slower rate, and eventually it plateaus, and it hits this maximum response level above which it cannot increase anymore. So as we saw in the last video, this shape of a dose-response curve is characteristic of dose-response curves. Again, if you want to learn more about dose-response curves, be sure to check out that video. It's in the description below. But what's very important to note is that this dose-response curve, this increase in response as we add concentration of agonist, and response increases and then plateaus, it does not start out from 0. It instead starts out from this point here, because remember, we have constitutive activity. We have like a default, like a base level of response, and it's above this base level response that the agonist can increase response even further. So we started at like 4, but then the agonist, you add it and it can increase response up to 10. And remember, these numbers are just arbitrary for learning purposes. They don't have any units, but the point is, it does not start at 0, it starts at constitutive activity, and it increases it beyond this level, and then hits a maximum. Also, ignore this full part for now, we'll get to that later. Okay, so now that we understand constitutive activity, let's talk about antagonists. So antagonists, they also go and bind onto receptors, and they occupy these receptors. But instead of like agonists, how they go and change the conformation of these receptors, antagonists actually don't change the conformation. So they go and bind onto these receptors, but the conformation of the receptor does not change. It just stays as it was before. So it simply basically goes and just, it binds onto the receptor, and it kind of just sits here and blocks the receptor. It prevents other things like messenger molecules from coming and binding onto it because it's in the way, it's blocking its spot, and it just sits there. But it doesn't actually do anything response related. It just kind of it keeps things as they were. The conformation of the receptor does not change, and as a result, the response inside the cell does not change. So when antagonists alone go and bind to receptors, the response just remains at constitutive activity. If a muscle was already being contracted at, let's say, 5 millinewtons on its own, then when you add an antagonist, it comes and blocks these receptors. Well, it's not changing the conformation of these receptors, so still the muscle is just going to be contracted at 5 millinewtons. The response levels are not going to change. So on the dose-response curve, if you add an antagonist alone, the response levels is going to look the exact same as, just normal constitutive activity, because it's not changing your receptor's conformation and everything's just going to seem as normal. There's not going to be an observable change in terms of response. So you guys may be thinking, if antagonists don't really do anything, they just kind of keep constitutive levels the same, then why are they significant? What's their point? Well, while they don't do much on their own, their effects become very obvious when they're used in conjunction with agonists. So here you have a cell with a bunch of receptors, and when you add antagonist along with agonist, then it becomes very obvious that antagonists play a big role. So remember what we said before, you add an antagonist, it will go over to receptors and bind to them, but it won't change their conformation, it's just going to sit there. If you remember in our last video, we learned that the process of stuff binding onto receptors is usually random or stochastic. What does this mean? Well, messenger molecules, they don't have a mind of their own. They don't selectively decide to go and bind onto receptors. No, they just move around randomly in all directions, and randomly, stochastically, by chance, one may go and happen to lock onto a receptor, and it's bound to it. But it doesn't last forever. After some time, it may leave and go somewhere else, and another messenger molecule can move around randomly and come and take its place. So all these messenger molecules are in a constant state of randomly moving around, randomly binding, and randomly leaving receptors, trading places. So their movement and binding and unbinding is all random or stochastic. And the same thing applies with antagonists and agonists. So your antagonists are going to move around just like your agonists, and they might randomly end up binding to a receptor, and they'll stick around for a while, and then after a while they will leave. Or usually they'll leave. Sometimes they don't, but that's an issue for the next video. For now, assume that they bind and then after some time they leave. So it's just like an agonist. But what's the problem is that now you don't just have an agonist. You have an agonist competing with an antagonist. So both of these things are moving around randomly in all directions, stochastically, and they're both trying to, they're both competing against each other to bind onto these same receptors. Think about it. Before you just had agonists, imagine you had a bunch of agonists. It's moving around. It's going to be able to bind to receptors. It'll leave, but something else will come and take its place. But now you have this thing in the way. What if your antagonist goes and binds onto this receptor? Well, now your agonist can't go and bind. Because you have multiple things at play here, the number of receptors that your agonist can bind to is effectively lowered because you have it competing against something else. Your antagonist is going to be taking up some receptors, taking up some space, so your agonist's activity is limited. And therefore, when you use an antagonist together with an agonist, the overall response decreases compared to if you had just used an agonist alone. And it's because the antagonist and agonist are competing each other. They're competing against each other. So now that we understand antagonists a little bit more, looking back at our dose-response curve, because we've just said that antagonists lower the response of agonists, you might expect a dose-response curve to look something like this for an antagonist plus an agonist. But that's actually not always true. Sometimes the dose-response curve for an antagonist plus an agonist can actually look like this. So just like your original one, but just shifted over to the right. Whereas other times it can be shifted down. And other times it can be both shifted to the right and shifted down. So it can look something like this. And the reason that these curves can look different is because there's actually different types of antagonists, but that is a problem for next episode. Don't worry about that for now. Now we understand antagonists a little bit better. Let's take a look at different types of agonists, like full, partial, and inverse agonists. So there's three types of agonists: full, partial, and inverse. The first one, full agonist, we actually already looked at it. The agonist we've been talking about this whole time is a full agonist. It's an agonist that binds to receptors and produces a full, complete response. Now let's look at what partial agonists are. Partial agonists, similarly to full agonists, they're messenger molecules that go and bind onto receptors and produce responses, but they're not as effective. You can think of them as having the effects of both agonists, but also the effects of antagonists. Now I know this might sound a bit weird, but the reason that I'm explaining it this way is because the real way that partial agonists work is very complicated, and it's outside the scope of this video. I fully don't understand it myself, so I don't think that I'm qualified to teach you. I would hate to teach you wrong information and mislead you. So for now, just think of partial agonists as having some agonist-like activity, but also some antagonist-like activity. But the general takeaway from partial agonists is that they are less effective than a normal full agonist. So therefore, it produces less response compared to, let's say you had a full agonist coming and binding onto a receptor, it would produce a lot more response. But when it's a partial agonist coming and binding, it will be a lot less response, or a bit less response. So going back to our dose-response curve, here this yellow line represents the activity of when you add your full agonist. You can see that it increases response, spikes up, and then it plateaus at your max level response. But then this green line represents your partial agonist. This also, when you add it and you increase it in concentration, it increases response above your constitutive activity, above your baseline levels, but the plateau that it reaches is not as high. It's only like 7 or 8 instead of 10. And that's because, remember, like we said, it has, well, you can think of it for now as having both agonist and antagonist activity. Reality is more complicated than that, but don't worry about that for now. But the general takeaway is that it's not as effective, so therefore its final response, its maximum response, is not as high as a full agonist. So we've covered full and partial agonists. The last type we have to look at is the inverse agonist. As the name suggests, inverse agonists have the inverse or opposite effect as a normal agonist. But you may be thinking, I thought the opposite of an agonist was an antagonist. But remember, antagonists, they just bind to receptors and sit there. They don't really do anything. And in fact, on their own, they don't really change response. Response just stays at your same constitutive levels. But inverse agonists, they actually do something on their own. They don't just bind to receptors and sit there. Well, an agonist increases response, so then an inverse agonist must do the opposite. It lowers response. And this is possible because remember the whole thing about constitutive activity. When a cell is at rest, when a cell is just chilling at its, baseline default states, response levels are usually not at 0. They usually have some level of baseline or default response. In the case of our graph here, the baseline response is 4. That is the constitutive activity of the cell. So because there exists like a pre-existing or like a baseline response level, that means that we can actually lower response below this level. Here we can lower response below this level. So we get a dose response curve which looks like these ones up here, except it's flipped over. And that is what an inverse agonist does. It lowers responses below your constitutive activity levels. So how does this work? How does a messenger molecule binding to a receptor lower an already occurring response? Well, so what it looks like is you have your inverse agonist, and it'll go over and bind onto a receptor. Now you see these blue exclamation marks inside your cell. That represents the constitutive activity, the response that's already happening at baseline. But when the inverse agonist binds, it's going to lower some of this response, lowering it lower than your constitutive activity. Now, again, I'm not going to really get into how this works because just like partial agonists, the mechanism is very, very confusing, complicated. I also don't fully understand it myself, and I would hate to mislead you with the wrong information. It's outside the scope of this video. If you really want to learn, I would recommend reading some research articles about pharmacology, inverse and partial agonists, to learn about the exact mechanisms of these different types of agonists. But for now, just the main takeaway is that inverse agonists bind to receptors and lower already occurring constitutive activity. Yeah, in the future, if I come to understand in greater, if I get a better understanding of how partial agonists and inverse agonists work, I'll be sure to make another video explaining them in more detail. But for now, unfortunately, this is the extent of my knowledge. But you can see in your diagram, this is what the response of an inverse agonist looks like. So just like all your dose response curves up here, it looks just like them except flipped over, and it lowers response from your constitutive activity as you add more inverse agonists, and then it drops, and then it plateaus, just like these also plateau, except these plateaus are basically your max response. Here, your plateau is basically your minimum response. And that's inverse agonists. So before we go out and end the video, I wanted to share this table that my professors put in one of their lectures when they were teaching me this concept in first year. And I found this really useful for visualizing the effects of all our different agonist types. So here's the table. Each of these columns represents a different condition. Well, the first column here represents concentration of your drug measured in micromolars. And then all of these ones represents different conditions. So let's put a little gap here between concentrations and conditions. First condition is no drug. So if you're not adding a drug, concentration doesn't really matter. And as you can see, when you don't add a drug, the constitutive activity of your cell is at 100, and this doesn't change. This is the baseline of your cell. Then when you add a full agonist, this is going to increase the response of your cell. So as you can see, when you have no concentration of agonist, nothing happens. But then as you increase concentration, the response steadily increases and increases. Just like how in your dose response curve that we have, as you increase concentration of your full agonist, response increases and increases. Eventually it plateaus, but this table, I guess it doesn't get to that part. It just shows the increasing section. Then you have partial agonist. This also, same thing, as you increase the concentration of partial agonist, response increases and increases. And you can see that both with full agonist and partial agonist, your response increases above your original constitutive activity of 100. It increases above 100. But your full agonist's response is definitely a lot higher compared to that of your partial agonist. And that's because, as we said, your partial agonist, it's not as effective as producing responses. The response levels are not going to be as high. And we can see that in our dose response curve. Our full agonist has higher responses compared to our partial agonist. Partial agonist still increases response above constitutive levels, just not as much as a full agonist. And then you have your antagonist. Now remember, your antagonist on its own, it just goes and binds to receptors and it just blocks them. It doesn't change the conformation of your receptors to produce or lower response or do anything like that. It just goes and binds to receptors and blocks them. But everything happens at baseline levels just normally. That's why no matter what the concentration of your antagonist is, no matter how much you add, the response levels are still going to be at 100. So this column is identical to when you don't have a drug, because antagonist on its own just goes and blocks receptors. It doesn't change their conformation, so therefore it doesn't produce a response. And this is synonymous with our dose response graph, where when we add an antagonist alone, the line is the exact same as constitutive levels. And the last one is inverse agonist, which we have in the table over here in this column. So you can see that the more concentration of inverse agonist you add, the lower and lower response gets. So it starts at 100, which is your constitutive activity, but then as you add more inverse agonist, it drops to 40, then 30, then 20, 15, 10, and it keeps getting lower and lower. So this makes sense. Inverse agonist lowers response. The more you add, the more it lowers response below constitutive activity. And this aligns with our dose response curve. The more you increase concentration of your inverse agonist, the lower and lower your response gets. Now, one really important thing to note with inverse agonists is that the more you add, the higher concentration you have, the more and more it will lower your response, but it will not get to zero. It can get close to zero, but it won't get to zero. The level of response, the level of activity in your cell, there'll always be a little bit. It cannot completely eliminate the cell's natural response. And that's why we draw the dose response curve like this. As you add inverse agonist, it lowers response, but eventually it plateaus. Just like your agonists, that they have like a cap of, max response they can produce, the inverse agonist has a cap of the minimum response it can produce. It cannot go any lower than this. Maybe you can find a stronger inverse agonist that has an even lower response. Maybe it goes something like this. It can get really close to zero, but it cannot quite get to zero. It cannot completely eliminate your cell's activity. And that wraps up this video. We have successfully covered full agonists, partial agonists, and inverse agonists, and antagonists. And we've also gotten a better understanding of constitutive activity. And we've gotten more familiar with dose response curves. So thank you guys so much for watching. In the next episode, we're going to learn about different types of antagonists. The type of antagonist we learned about today is called the pharmacological competitive antagonist. But there's competitive and non-competitive. There's pharmacological and physiological. There's surmountable and insurmountable. There's all sorts of different types of antagonists. That is next episode's issue. But for now, thank you again for watching. I hope you understood and I hope you liked the video. I hope it helped you learn. Any questions or comments or suggestions, please leave them in the comments below. I'm willing to take any and all feedback, and I will make changes or I'll take requests and make videos if you guys would like. And I'll see you guys next time. Take care for now.